Hello YouTube. In this video we're going to be discussing specifically how we multiply numbers, but numbers that are listed in trig form, that is complex numbers that are written in trig form. So very quickly before we look at the theorem, or at least the law for multiplying numbers in trig form, let's review what we mean by a number in trig form. That is, given some number x plus yi, that is some complex number, we can graph this in a rectangular sense by saying, we would deviate x to the right, and then up y units, but we say y and x, and we say that it is some vector, this vector here, this arrow vector, and we call this vector its length r. But we say we could classify this number right here by telling you two things. First of all, we could tell you how far to rotate in standard position, some angle theta, and then how far out to walk from the origin to get to that point. So we say any number in trig form can be listed as some modulus or length r times cosine I sine, we typically just write cosine I sine, of some argument theta. In other words, we just need a direction and a distance to walk from the origin to get to that point going in that direction. So, anyways, that being said, it is very, very actually convenient to multiply numbers in trigonometric form. And we use this law up here. So we say, let our first complex number, we'll call it z1, equal modulus 1 times cosine of theta 1 plus I sine theta 1. Okay, so this is our first complex number with our first argument and our first modulus. And we say z2 is just simply our second modulus and our second direction. But when we multiply these two things, that is the product of z1 and z2, the important thing to note here is this. We just multiply the moduli. That is, we'll take r1 times r2, and we get our new r on our product. And then furthermore, we say, well, whatever our first argument or angle was, theta 1, and what our second argument was, theta 2, we can just simply sum these two angles. So the convenient thing about multiplying numbers in trigonometric form is just this. You just multiply the moduli and you add together the angles. It's a really, really easy thing to do. So what we're going to do is we're going to do two examples. In the first example, I've already given us two numbers. We call this one here z1 and z2, but we're going to find the product of z1 and z2, and these are already in trig form. And then we'll go over to another example where we have two numbers in standard form and talk about why it would be much easier to multiply them in trig form as opposed to standard form. So let's go ahead and take a look at this first example here. We say 3 cis 40, or 3 cosine I sine 40 degrees, and 5 cosine I sine 10 degrees. In other words, we're saying basically here we got a 40-degree direction. We're going out 3 units in that direction. We say, so this number here times 5 cosine I sine 10, if 10 was like this angle here, and we're going 5 units out, we're basically finding the product of these two numbers. But we're saying that the product of these two numbers is simply the product of their moduli. So we say 3 times 5, so we get the product here, z1 times z2 is equal to 3 times 5. And then this is cosine I sine of 40, which is our first argument, plus 10 degrees. So, I would never really write it out like this, but just to kind of show you how this law works, I've written it like this. But we say basically what you get is you get 15 cosine I sine of 50 degrees. And so you'd get this new number, which we'd say is at a 50-degree angle, which would be maybe up here on our diagram here, and we'd go 15 units in that direction, and we'd get this as our product. So now, I want you to know we could have done the same thing with standard form. However, standard form is a little bit more drawn out, literally and figuratively. So let's go ahead and take a look at this second example up here, example B. What I've written is this. I'd like to find the product of these two numbers in standard a plus bi form, and then what we're going to do is we're going to convert these numbers to trig form and find the product again, just to show you how much more convenient it is to find a product when you have numbers in trigonometric form. And then we're going to compare our answers and just show that they are equivalent. So let's go ahead and take a look at the two numbers we have here. We have our first complex number, 1 plus radical 3i, and our second complex number is negative radical 3 plus 1i. There's a 1 in front of this, okay? So the first thing we want to do is actually find this product we said in standard form. So what we get is 1 times negative radical 3 is negative radical 3, negative radical 3. And we say 1 times 1i is plus 1i. We say radical 3 times negative radical 3i. Well, first of all, this can be negative. And radical 3 times radical 3 is 3, so we get 3 i's. And then our last product here, we get radical 3 I squared. So we'd say plus radical 3 I squared. So a few things we can say about this. First of all, if we combine these two middle terms here, we end up with a total of, let me write that negative radical 3, a total of negative 2 i's. And then on the right here we say I squared. Well, that I squared is equal to negative 1 if you know anything about complex numbers there. And so what this does is it just flips the sign on our radical 3, so we say minus radical 3. And so the convenient thing here is we have negative radical 3 and negative radical 3. Negative 1 radical 3 and negative 1 radical 3, those combine to give us negative 2 radical 3 is our real part of our complex product minus 2i. So we're going to put a box around this. Now that wasn't so bad. But then again, like, I'm biased here, and I don't like to FOIL if I don't have to. So what we're going to do is we're going to convert these two numbers to trig form. So recall, trig form means that we have to have just a modulus, or at least a length, from the origin out to the point, and then a direction to head in. So this first number here, we say 1 plus radical 3i. There are two formulas we need to keep in mind here. If we needed to find r, we could say r squared is equal to x squared plus y squared, or in general, we say r is just the radical of x squared plus y squared. That is the length of our modulus. And we also know this, that the tangent of theta, looking at our diagram here, tangent of theta is y over x. So tangent of theta is y over x, and it can be implied then that we could say theta, therefore, is the tangent inverse of y over x. So we just need r and we need theta, and so we're going to do this for both numbers here. So we say, well, looking at our first complex number, we would say r is 1 squared plus radical 3 squared. So we say r1 is square root of 1 squared plus radical 3 squared, which is the square root of 1 plus 3, which is the square root of 4, which is 2. So this is our r1. And then we say, as far as our argument goes, we could say then theta, or at least theta party hat, or theta prime, or theta, what this thing is a reference angle, we could say is tangent inverse of y over x. And in this case, our y value is radical 3, and our x is 1. And we know that, well, we should know that theta, therefore, is 60 degrees because the tangent inverse of radical 3 is 60 degrees. So we say 60 degrees. So now we could say our first complex number in trig form is this. We have 2 CIS 60 degrees. That's our first complex number in trig form. So now let's take a look at our second complex number in trig form, which is negative radical 3 and plus 1i. So if we find the modulus of this number here, that is r2. r2 is equal to the square root of negative radical 3 squared plus 1 squared. So we get, again, 3 plus 1 in here, which is radical 4, which is 2. So the modulus of our second vector is also 2. So we could say, okay, so 2 CIS. Now we just need the argument for the direction. And so we'd say, okay, so theta, therefore, at least theta party hat, or theta prime, or the reference angle, is tangent inverse of 1 over negative radical 3, or y over x. So in this case, this actually rationalizes out to be a negative. First of all, tangent inverse of negative, and second of all, radical 3 over 3. So whenever you take tangent inverse of radical 3 over 3, you're dealing with some sort of 30-degree reference angle. So we'd say 30-degree reference angle. And you know, if we're considering that that's our reference angle, we know that this number right here, if we were to graph this and say standard form, we'd say that we'd go left radical 3 and then up 1. In other words, we're up here in the second quadrant somewhere. So if we're saying that this angle here, which is our reference angle, is 30 degrees, what we need for an argument then is this angle in standard position, which would have to be 150 degrees because 150 plus this 30 here gets us over to 180. So we say our argument here is 150. So now, I am not advocating for actually, if these numbers are in standard form, putting them into trig form and finding their product. I am advocating for this. Just go ahead and multiply numbers in trig form if at all possible, because it's much easier to do. So what we wanted to do in the first place was actually find the product of these two numbers. So what we say is, if you're multiplying two numbers in trig form, up here on the left we say you multiply them modulate. So we get 2 times 2 is 4. And we get CIS. CIS of what? Well, 60 plus 150, we get 210 degrees. So now what I wanted to do in the beginning here was compare our two answers. So in order to do this, what we're going to do is we're going to convert this standard form. Actually, no, let's just convert our trig form number back to standard form. So this would be 4 cosine 210 plus I sine 210. 210. And so we'd say, okay, so this is 4 times cosine of 210. Cosine of 210 has a 30-degree reference angle. Recall that 210 is like 30 degrees past 180. It's right here. It's a 30-degree reference angle. So cosine of 30 degrees is radical 3 over 2. And since it terminates in the third quadrant, this will be a negative radical 3 over 2. And this will be plus a negative, because sine is negative in the third quadrant as well, but this will be a half I. And so if we distribute this 4 here, we actually get negative 2 radical 3 when this simplifies, plus negative 2i, which should look familiar because this is precisely the number that we were dealing with up here. So the point of this video, of course, is this, that you can multiply two complex numbers in trig form just by multiplying their moduli and then adding their arguments. And that's simply it. And that should be simple. So let's keep it simple. But yeah, it works. Enjoy.